Hey everyone, let's start with a quick, I would say a word quiz, but it's not graded quiz, rather, I'm trying to integrate a little bit of those, questions that you asked me to have at the beginning of the lectures. So this is just a little survey for BPE stuff. So let's take maybe just a few minutes, 2 minutes to quickly solve these 3 questions, and then we are going to go over their responses, and hopefully this time I didn't see what the majority vote is. Okay, this is like a little ungraded survey. See? Okay. Okay, I will get started. I see not everyone is done, but we can't spend too much time on this. So, if you're wrapping up, can you just click something to wrap it, and then I will lock it. There's more than 23 people in this room. Okay, I will lock the survey, and let's go see the answers. Okay. So the first question was, how are units for what we're going to place in the vocabulary of BPE chosen? And I gave you different options. And for the most chosen option here is that this is going to be decided in a data-driven way, and these units are going to be subwords. So this can be characters, morphemes, words, or something in between, right? Like they do not need to be linguistically motivated if it turns out that that subword is the most, common merge that we need to do in a given step. So the other options are not true because I emphasize here exclusively, right? So although your token in your vocabulary, repeat vocabulary might be a word in the end or a character, it's not that we end up with exclusively characters, morphemes, or words. So please, if you have selected those other options, this is an important bit to remember that BPE is learning the vocabulary in a data-driven way, not by us manually deciding what the units of the vocab are going to be. Okay, now the next question was, we are training a BPE and we are at a merge operation where we need to merge occurrences of O and R. And the question was, if we do that, that iteration of BPE, what the output is going to be here. Again, the more often chosen option here is the correct one. And here the intent behind the question was that I test whether you remember that we are not crossing the word bound, right? So yes, it is true that hello ends with O and a robot starts with R, but we are not going to apply that merge operation, right? Because we would cross word boundaries. There's also another issue here with the second option, where now I have created, basically, I kind of created a whole new word out of the original words. When you are implementing this in your homework assignment, I recommend that you are tokenizing each word word by word into subwords. So you would never see something like this. So here, the most important bit to remember is we are not applying merge operation across word boundaries. That's important. And just as a reason why, we do want to remember the word boundaries so that our models don't need to remember that, which is the problem we had with characters. Okay, final question was about what is the size of the final vocabulary. So we start with some data. This data, the first step of BPE will be to basically split each word in the data by characters, right? And then we are going to start to merge this character and eventually tokens that are composed of more than a single character. So initially we start with 45 unique characters, and then we perform 512 operations. The resulting vocabulary will be of the size of the number of unique characters in the beginning plus the number of merge operations we had, which means that we will end up with the, did I give you a right option here? I did, the last one, 557, right? So that's going to be the final size of your vocab. There's a little detail here that I didn't mention last time, and that's basically because we are learning the merge operation at the word level. Eventually, if you had chosen a very large number of merge operations, there might not be anything to merge anymore. So you will end up with the vocabulary size of like maximum what's possible. But if you don't do that, which you should not, because then you will end up with words being the chosen tokens in the vocab, then you want to learn subwords. So you don't choose a very high number of merging operations. Then you will always end up with the number of unique characters observed in the data plus the number of operations. Yes, please.
There's one size thing I'm a little confused about. Between BPE and, say, the whitespace tokenizer, does BPE end up having a larger vocab because you're doing the characters plus these merges, or will whitespace have a larger vocab?
Yeah, this is an important question, and the answer is that the word whitespace tokenizer would have more tokens in the end in the vocab if we are working with a very large whole. So let's imagine we are training our or producing our vocabularies from a very, very large corpus. Then there is going to be more words than what we set the number of merges hyperparameters, hyperparameter value to be. So we are in control how many tokens we will have in the BPE tokenizers vocabulary, right? Like we set the hyperparameters value. And we won't set it to be so high that we end up with all the words.
Okay, so could we say that for BPE versus whitespace, if we're dealing with a large enough corpus, would there end up being more words, i.e. more tokens for the whitespace compared to the total number of characters as used in BPE?
Not characters, but tokens in BPE. So
characters then leading into
yeah, that's right. We are going to design BPE tokenizers to have exactly the situation you have described. And then remember the reason why. I said that in the end, we need to have that output layer, and the size of that matrix is going to be the size of the vocab times the dimensionality of our hidden representation. So if you have a huge vocab, you need to have a huge output layer, and you need to store all these numbers somewhere, which we will be bounded by hardware, which are GPU memory.
Okay.
Yeah. Okay, so here other options were just distractors. This one is 22,000. I just made up. The other ones were some combination of these numbers in the input. So if you haven't chosen the last option, remember, unless I give you a very high number of merge operations, you are going to end up with the number of unique characters in the beginning plus number of merging operations as the size of the book. Okay, so these are some bits and pieces that just kind of course, it's not all we need to remember about BPE, but like if you felt like you haven't answered these questions correctly, I recommend that you review that lecture, and that's going to be the case every time I bring polls like this at the beginning of the lecture. And then your whole assignment that you are working on is about implementing BPE, so you have another chance to kind of dive into that algorithm. Okay, we have lots to talk about, so let's move forward. Remember that last time I gave you a little preview of what's coming next in the course, and first thing I said is we are going to stop doing the white space tokenizer and learn better way of tokenization. Great, that's done. And now we need to go into our other issues, which was like, oh, our word order is completely ignored with previous neural networks. Our embeddings are always going to be static regardless of whether a word has multiple senses or not. And if we have very long context, are we really going to remember what's going on at the end of that input relative to the beginning? And today we are going to introduce an architecture that's going to help us with these problems. We should address them. And just as a more like setup for what we are talking about, remember that now we are trying to see how the LLM and chatbots based on LLMs like ChatGPT go from a prompt to a response. We have said that first thing is always going to be to tokenize input. These tokens will have their indices in in the vocabulary. And then we are going to map each one of these tokens into their token embedding. We are still going to do that, but we are going to find from that initial token embedding a new hidden representation, a new high dimensional vector, which will have two important properties. The more important one is that this new representation is going to be contextualized, which means that now this new vector for a given token is going to contain information coming from other tokens in the input that are important for understanding that token. So maybe I can illustrate that with the subject-verb-object relation, right? These tokens are important to each other to understand the grammatical structure of the sentence, right? So when you're processing a subject, knowing what the verb is might be important. And now with this architecture, you will have a chance to take information from the vector of that other important token and kind of mix it up with the representation of the current token for which you are producing a nice vector representation. And of course, we are going to stack this, so we are going to have some nonlinear operation, because remember, we like nonlinearity because what was impossible in original space becomes possible in this tweaked, deformed new vector space. Okay, so that's what's going to happen next. This architecture that I'm going to introduce called transformer. Let's do the test of time. Before I go into what's next, can you raise a hand if you have been taught about transformers in details before? So we have four, and two you have. Okay, so most of you haven't been taught about it before, and that's okay, because we are going to go in extreme detail here, and you're also going to implement this architecture as your last assignment. So again, pay attention. What I wanted to say here is that Transformer has stood the test of time. It's architecture that has been introduced in 2017, and unlike those that have come before it, in this new wave of deep learning that started in 2014, it's still around. It's still something you will see in the state-of-the-art large language models. Prior to that, every field of modern machine learning had its own neural architecture. That was kind of the best performing architecture for that modality. So we have seen that previously I mentioned for neural machine translation, recurrent neural network was or instead of mergent LSTM was a thing we were using. On the other hand, in computer vision, convolutional neural networks were used, a very different kind of neural architecture. And then in RL or speech, you had something else. And then that completely changed with transformers. Transformer is now a neural architecture that you will see used in many different application domains, from vision to natural language processing, speech, and so on. So it became kind of like this unifying architecture that also had enabled us to have later multimodal models. So for example, when you use ChatGPT, you can give an image, right? And there is a speech functionality and so on. Having a unified architecture helped with that. Now, this is a visualization of Transformer from the original paper with a classic title, Attention is All You Need, or I should say iconic title. There are so many variations of this title now in the literature. And I'm not going to lie, the first time I have seen this, I was a PhD student, I was tired, and I saw it, I was like, oh God, hopefully this is one of those that dies, and I just don't need to learn about it. Year later, I was like, okay, not gonna escape this one. So I had to force myself to learn it, and good for you, I learned it really well. So we are going to cover it today. But it does look a little bit daunting, especially given what you have seen in the course so far, when we have played around with more simple neural networks. Okay, so let's dive into it. I'm going to first give you the most zoomed out view of Transformer, and then we are going to go deeper and deeper and deeper. Okay, so at the highest most level, Transformer, the way it was originally produced, not necessarily anymore, is an encoder-decoder architecture, which is great because we have learned what that architecture is, right? We have learned that it takes some input sequence, and encoder part encodes this sequence in a vector representation, and then our decoder takes that representation and starts to decode, meaning generate token by token new text. Now, as the figure I have first shown suggests, it's not simple as that. So in encoder, that big visualization of encoder is actually a stack of encoder blocks, and decoder is a stack of decoder blocks. Then each encoder-decoder block has its own composition. So we are zooming in a little bit more. Here, encoder block have two main components. One of them is called self-attention, and the other one is going to be our feed-forward neural network. We're kind of maybe now starting to feel a little bit better because we have heard about attention before. We have heard about feed-forward neural networks. So although at the highest level maybe looks complicated, now you are starting to see something you have heard before. So now I'm going to explain you in all the details what self-attention is, because it is the most important bit of the Transformer architecture. Okay. And for that, I'm going to use a whiteboard. See, is that what comes next? Okay. Before I go into derivations on the whiteboard, I want to remind you of one of the issues we have, which is that we have words that can mean different things, that is, have different senses, depending on how we use these words, right? Like Bayesian here. And our problem with token embedding so far is that each time this word appears, regardless of its sense in a given text, we use the same static token embedding. Whereas it would be better that we look around a little bit and see what else is in this input. And upon seeing word like Amazon in the first example, we would tweak the token embedding of Bayesian to capture that we're talking about a particular sense of that word. And this is exactly this what I'm describing now is what self-attention is going to help us with. Okay, so let's get into it. Our goal is to map each token embedding to a high dimensional representation that captures information about other important tokens in the init. Okay. Writing on this board really takes forever, which is the point. It's incredibly visible. All right, and we're going to see how attention works, how we can do this through an example. I'm going to give you a very short sentence of only two words to make this easier to go over. So imagine your input is thinking machines. And I'm using this example because it's used by the blog whose visualizations I have been used previously, so you can easily match them. Okay, so first thing, imagine these are actually tokens, although we have just learned about subword tokenization. Imagine I'm tokenizing this, meaning I would end up with a list, right? The first thing we are going to do, we are going to have some token embeddings for each one of these tokens. So don't worry yet about how we get those. You can think about standard things, you know, like word-to-vec embedding, but we're not going to be using word-to-vec embeddings anymore, but these are just going to be, again, you are going to have your embedding matrix, like you always had. That's going to be first layer to the transformer, and then you can do token lookup, right? So this is my input, embedding lookup will give me from my embedding matrix, I'm going to get embedding of thinking, I'm going to get embedding of machines, and I'm going to write a little bit more Pythonic annotation. I'm going to create a matrix out of these two. So I'm going to stack their token embeddings row-wise. So this is going to be element of L, where L is input length, so 2 in this example. Times some dimensionality, I will call D1. Okay, so here, the first row corresponds to embedding of thinking. And the second one is embedding of machines. So far, nothing special, nothing super new. We created our inputs. That's it. Okay, now is where, next step is where things are going to become different from what we have seen before. So basically what I'm going to do next is take my input X, and I'm going to linearly transform it 3 times with 3 different transformations. No, not 2, we skipped 1. Okay, if I would like to transform X into D2-dimensional space, so each vector in X in D2-dimensional space, what do I do? Say? Multiply by weight matrix. So here X is going to be in L time D1, And I want to preserve that L is my leading dimension, length. So I'm going to multiply this from the right with some weight matrix whose dimension is going to be what? Yeah.
D1 cross
D2. Yeah, that's right. So here, I'm going to give this weight matrix a special name. It's going to have this superscript Q here. And the matrix I'm producing is going to be called query matrix. Well, query matrix. Here, Q is going to be in R D1 times D2. Okay, and I'm going to, as I said, do this 3 times with different transformation. I'm going to produce so-called keys, which is going to be just another linear transformation defined by another set of weights, WK. And this is also going to be in D2, D1, sorry, by P1. D1 by D2. And we are going to also have another transformation, which is called values. Okay. I'm going to explain why exactly we make these 3 transformations in a moment. It's going to be clearer when I describe what's coming next, okay? Did we capture this? Oh, sorry, go ahead.
How are those weight matrices initialized, or will we cover that?
They're going to be in a transformer, vanilla transformer as it is defined in 2017. They're going to be random weights, and you're going to use Laurent-Xavier initialization as you have before. However, our next topic in class will be that we are going to so-called pre-train these weights, and then when we use them, they're going to have special values. They're not going to be quite random, but that's another topic. Okay. Okay. I don't need to take a photo because I have a slide with this. I'm trying to keep the seat benches within at the top because we are gonna need it. Okay, the next step is where things get interesting and what self-attention is all about. So in the next step, we are going to learn what are the pairwise importances between tokens, like how much some token in the input is important to another one. And for that, we are going to use these linear transformations we have just introduced. So in this step, we are producing so-called attention metrics. One of the most important equations you will see in machine learning papers, recent ones. Basically, the way we can produce importance of one token to another token is to take a representation of that token and make a dot product with representation of another token, right? Like in this course so far, the notion of importance was always, if I want to measure importance of 2 things, take their recurrent vector representations and do the dot product, right? So basically, what I'm going to write next is just a concise way of writing a bunch of these dot products. So the thing I'm writing is take my query matrix and what is the shape of the query matrix? Query matrix Q.
L by D2?
L by D2. So I didn't emphasize that above, but basically Q and each one of these matrices above is containing a representation of the same input tokens, thinking and machines, okay? So they are just different representation of these tokens. So we have in X initial token embedding for thinking. We have in our query matrix in the first row another representation for thinking. In keys first row, we have another representation for thinking. In first row of values, another representation of thinking. Okay. So there is that times K transpose. Here our keys matrix also has first row a representation of thinking, second row representation of machines. Now we just did the transpose, so we can do product of these two matrices. And when you if you were to write it down, this matrix multiplication, you would see that basically what you're doing is dot products between the representations of these tokens. So we have here as a way to visualize it, so thinking and machines, and then here two columns. One is for thinking and the other one for machines. I end up with L by L matrix, right? And then the value here is produced by taking the embedding the representation of thinking in my query matrix and multiplying it, not multiplying, but doing the dot product with the representation of thinking in the keys matrix. Here, I'm taking, for the second value here, I'm taking the representation of thinking in the query matrix, and I'm multiplying, again, sorry, dot product with the representation of machines in the keys matrix, and so on, right? So basically what I record here is these importances of one word to another. So let me write it differently. So TT means how much thinking is important to thinking. So it's always going to have pretty high value because, of course, that's the information we have in the beginning. Then how much machines is important to thinking, how much thinking is important to machines, and how much machines is important to thinking. Okay, now, as we talk about importances, and I tell you that this can be any real number, what do you know I'm gonna say next? Yeah, softmax, I love that. Yeah, like we don't want these values to be from minus infinity to plus infinity, because then what is really important becomes a hard thing to answer. So the thing we are gonna do is we are going to take a softmax and I'm gonna apply it row-wise, right? Like softmax takes a vector, produces a vector. So we can't take a matrix, rather we apply it row-wise to this product. And here, I'm just going to write this term, the square root of D2. This has been empirically found to be important for stability of training. So this is here, there is nothing super important conceptual wise. This is just an empirical addition. Okay, so don't make too much fuss about this one. This is important. Okay, and now what I will get are values between 0 and 1, and I will have again a square matrix L by L. I'm going to quickly show you just one example of, I'm going to show you a bunch of visualizations later, but here is an example of how a heat map produced by one of these matrices. Here the input is he was becoming agitated, ignore his special CLS and separator tokens. And what you can see here is that for the token he, it turns out that the tokens becoming agitated have quite high importance. And the reason for that could be that this attention mechanism is specializing to capture something like subject-verb relation. We can just hypothesize, but maybe this is if we have seen a lot of these matrices across many inputs, and all of them are quite have very high values for main noun like subject and a verb. We can make that hypothesis. Okay, any questions about this? Oh, yeah, many. Okay, let's start with you.
Is there any reason why the diagonal doesn't have very high importance? Like, is there anything that does that? Like, I guess that.
In this matrix, turns out there isn't, but actually across many of these matrices, you will see that diagonal elements and near diagonal have very often very high importance. And the reason behind that is language is local, in a way, right? There are some phenomena, and especially in some other languages than English, where you would have this huge long-range dependencies, but importances and in a common grammatical structures, very often they will be very local. So this is a very particular example where it turns out that the diagonal is a superstar. Yeah. Billy, you have a question?
Yeah, I had a very similar question. I was asking why, like, for the same word, you don't see high similarity, but is that because you're multiplying it by a different weight matrix?
No, I wouldn't say that. So again, I think here, as I just said, you would see a lot of importance on the diagonal very often. Turns out that here it isn't so important. And then again, we are not making any manual intervention. So these weights of the query key and values are going to be learned from the data, and they on their own will start to specialize for something. Now you can tell me, well, if they're specialized for one feature of the language and there are so many important ones, how is this going to work? And the answer will come in the next slide. Let's first look at
D2 in this case, a hypergram.
Yeah, that's right. So always the dimensionality of these things are going to be hyperparameters. So D1 and 2 is something that the creators of this architecture choose. Later, when we start to talk about pre-training, we are going to be stuck with whatever these choices, and we won't be able to change them. Yeah.
So what exactly do queries, keys, and values mean in this context?
Yeah. So yeah, that's a great question. Thanks for reminding me. I didn't go over like why exactly are we making these transformations. And I'm going to give you an intuition, but what exactly they're doing, that's a whole other question to confirm that the intuition is right. But basically what we are trying to do by, I will reframe the question differently. Like, so you might ask me, why don't we work with the X directly? Why do we need to linearly transform it and then do these dot products, right? And the idea is that by transforming them, they have a chance to specialize for something. So a query, a vector like in the original attention we have talked about already, is the one that is looking for important information, right? So you can imagine that with this particular query weight matrix, the model is learning to look for something specific. So for example, if a given token is a noun and that's somehow captured in the embedding of that token, didn't say to the model explicitly, this weight matrix can specialize for, I'm going to look for all the verbs in the input because I want to capture subject-verb relation, right? So it's creating a representation that might very extremely emphasize this is a noun. On the other hand, our keys, the thing we are attending over, they are maybe also can, with this transformation, have a version which will be specialized for emphasizing whether this token is a verb or not. So if you're getting lost, that's normal because what we are kind of trying to achieve with this is having these kind of different ways of capturing different linguistic phenomena. But then again, it's not like anything encoding this up made that explicit, right? This is just the intuition and behind this linear transformation. What exactly happens is a complicated question, and that's why interpretability of this thing is a huge, complicated topic on its own. Yeah. So from everything I said, I would just remember that we're doing 3 different transformations. We have a chance that the single attention matrix is capturing something particular. And as I hinted for the previous question, we're actually going to have many of these. We are going to have many of these at every encoder block. And we are going to have, let's say, 16 encoder blocks. In each one of these, we are going to have 8 of these and combine them in some way, which I will mention in a bit. Yeah. Okay, so, right, we have now measured importances. Does anyone remember what the main goal is? Given a token, what I want to do? Yeah.
Measure the relative importance.
Measure the relative, I just done that. So what's next?
Find what was asking.
So it's like, okay.
You actually asked me, what is the goal after this?
Yeah, so I have measured the importance of between tokens, but I had other goals in mind. I wasn't saying I would just measure the importance, I was saying I would do something with each token that is.
Is it to get more accurate embeddings for based on the components?
Accurate is a strong word. I don't know whether it's, hopefully it will produce something that's better, but what's really accurate, I can't really say. But you are hinting on something which is, we want better representation, but better in which way exactly?
Is it getting contextual about it?
Yeah, we want to contextualize, given my current token embedding for a word, I want to produce a new token embedding, which will have this information from the context. And I'm going to integrate information from the context based on the importances of each token of that token. So the way we are going to do that is by doing just another product. So in the end, I want to end up with a matrix in of the shape L by D2. I'm going to start with my attention matrix, and I'm going to multiply it with my vectors. Okay, so let's go over what does this mean. Here I will have my, TT, TM, and so on, MM, and MD. It's important that you can read the attention matrix. So here, first value, how important thinking is to thinking. Next value, how important machine is to thinking. How important thinking is to machines, and how important machines is to machines. So that's what we have in our attention matrix. And then we have our values. And as it was the case with queries and keys, each row here is the representation of an embedding in the input. So again, this is a representation of thinking, and this is another representation of machines. And my goal is to get another representation of thinking and another representation of machine, so where I have combined some stuff I have seen in vectors of other tokens. How does this product achieve this? Now, you need to be very comfortable with remembering like how we do matrix multiplication, right? So we are going to end up with the 2 rows again and D2 dimensions. But let's try to visualize together. How do we get that? So here, let's look into this value here. So this value, let's call it V, actually, let it be like V11. We are going to take how much thinking is important to thinking, and we are going to multiply it by the first dimension in the representation of the thinking. So trying to write this down in a way which will make sense. So I will write it like this: V1 of thinking. So imagine this whole row. First row is V of T, so representation of the thinking token. And then I'm going to take how much machines is important to thinking and multiply it. Now here is the important bit. I'm going to take a first dimension in the hidden representation of machines. Okay, so that's a very crucial thing to kind of imagine in your head now. I have taken basically a weighted sum to produce ith dimension of a hidden representation of thinking. I have taken a weighted sum of ith dimension of each one of the tokens in the input, where their weight was determined by attention. Okay, so if here I had 0.8 and 0.2, this would say, well, to capture whatever the first dimension in these vectors captures anyway, I'm going to take most of the original's token, first dimension, but I do need to know a little bit about this other token. So I'm going to take 0.2 of that. Or if you had 50-50, that would mean, well, both of these tokens are crucial to understand that given token I'm trying to produce the representation of. Okay, I will do it just one more time for you to kind of have a chance to go over this one more time, because as I said, it's important. So let's say we are here. So we have V of 1, 3. Oh, I can't let this one. I don't like that it's so low. Maybe if I write it here, V1, 3 is going to take the value of how much thinking is important to thinking, and then take the third dimension in the hidden representation of thinking and combine it by how much machines is important to thinking, and take the third dimension in the vector of machines. Okay. I hope this clicks for you, seeing how these representations are becoming mixed together to produce a representation of each token. Yes, please.
Just to clarify,
Yes.
this is a dot product that we're doing between these two versus matrix multiplication, which is what we're doing in step 2 above there. Because A's dimensions are L by L and V's are D1 by D2. So I'm a little bit confused how we get to L by D2 if D1 doesn't have a dimension to match up with.
In the end, we end up with L by D2. So why did you mention D1?
Because V, our value, wait a minute.
Values are gonna be D2. Where are they? Yeah, so here,
Oh, right.
yeah, all of them are gonna be.
They're L by D2.
Yeah,
Okay, I got mixed up with the weight.
Yeah, yeah. Yeah, that's just a little typo. Yeah, we are going to end up with the D2 dimensional vector for each representation, but we are going to now also transform them into D1 dimensional space. Okay, I'm going to visualize this. Then we are going to, in different ways, then we are going to complicate this if it wasn't complicated enough. So this is just another visual representation. Oh, sorry, you had a question.
So the V, there's the value matrix.
Yes, this one is value matrix. Yeah.
V, do you have a name for the result matrix?
No, but we will need it. So let's call it Z, but it's not important. Yeah. So Z, super unimportant symbol. In literature, A, B, Q, K, always used. So all of except Z are unimportant. Z is the only one which you can use whatever you want.
And we use Z in place of B on the board, correct?
No, we are using Z as a product between A and 2 and V. Z equals A times V, right?
Yeah, and when we multiply A times B, we get C, so on the line just below, is that, would that be C1?
Yeah,
Just for clarity.
yeah, I see what you mean. Yeah, yeah, yeah. Mhm.
Okay.
Yeah.
Okay.
Yeah, that makes sense. So here we would have Z and yeah, thanks for catching that. It's better we give this other names. Yeah, that's a good catch. Yeah. Okay, so I will just go over just to repeat everything. I'm just going to show you some visualizations. So again, we start with our input X. We then linearly transform it with 3 different transformations into query, key, and value matrices. And blah, blah, blah. Then we calculate attention metrics, which gives us in each row, we have how much are all the tokens in the input important to the token corresponding to that row. So we have distribution row-wise. And then we produce this new contextualized representation for each one of our tokens by multiplying attention matrix with the value matrix to produce which we just called Z. In Z, again, each row will be the new representation of the corresponding token in the input, but now it's going to be contextualized. Now, we are going to, this is another visualization. I'm just trying to show you all kinds of different visualization for if this wasn't clear. So this one, again, input X, you have different ways, produce different representations, do these products to then produce the final value, which is Z. However, what I wanted to get at, in each encoder block, self-attention will consist of doing this many times. So something like 8 times, right? So here I have shown you one attention head, okay? This whole thing we have done, it's called attention head. And we are going to do this, let's say 8 times with different set of weights for query, keys, and values. Okay, I'm going to write that down somewhere. Okay, and I kind of didn't give you intuition for that. Oh, this might go handy. But the reason why we do that, as I kind of hinted to my answers to your questions, is that each one of these set of 3 weight matrices, query, key, and value, is going to, the idea is that it specializes for finding some notion of importance in language. So one, as I keep mentioning, can be one attention head can be specializing for measuring whether giving importance to between subject and verb, and everything else is not as important. Other metrics can be, for example, for the problem of, let's say, for reference resolution, which is a classic task of finding which mentions of entities refer to the same entity. So, for example, if I say John was walking, he fell, we want to understand that he refers to John. And so one of these heads can have high importance only between entities and all of their mentions, okay? And so on and so on. So there are so many linguistic phenomena we could mention here. The idea is if we over-parameterize the model like this, give it a chance in each one of these encoder blocks to learn these different features, a lot of useful features will be learned. And I can tell you immediately there's going to be a lot of redundancy. So the number of these is set to something high, and later when we analyze and visualize these, we can see that 2 heads basically are doing the same thing. But when you create new neural architectures, you start with not caring about like everything being stripped down to most important components, rather doing something that can work really well, which often means adding more than you need. But multi-headed attention is gonna be around, so not something we have removed in the modern LLMs. Okay, so this is here. This whole thing is just one attention, corresponds to one attention head. With multi-headed attention, which is very often written as MHA, we are going to have a bunch of these, right? So we are going to have a set of 3 of these weight matrices, WQ, WK, WB, and there is going to be a few of them. So here I'm going to write I goes from 1 to 2 and heads. Sorry, I know you probably don't see this paragraph from me. So I'm just producing a bunch of these triplets of weights. And then each triplet can give me, now I'm going to just add subscripts here. Query I, key, keys I, values I produced with the corresponding weights VI here. So I'm just adding I's here, okay? And when I do, attention, and then I will get Z equals A times V, I will get from each one of these sets, I'm going to get different output ZI, okay? And what I'm going to do, I'm going to concatenate all of these ZI. So imagine each one ZI contains in each row a hidden representation of a token. If I concatenate them row-wise, I'm going to get for each token number of heads times the 2-dimensional vector, right? So the way I would recommend thinking about it, imagine imagine each row in each one of these outputs of attention heads containing some features learned by that attention head. And you are concatenating them all together in this enormous vector, which contains all of these useful features, okay? So I'm going to concat Z1 all the way to Z number of heads. What's the dimensionality of this one then? If I concatenate column wise, yeah.
And hence by D2.
Is that rows or columns?
Column.
Columns, right? And the leading dimension is going to be L. So n heads times D2. Okay, this is now a huge representation for each token, and we want to downsize. And we want to downsize to D1 that we started with. It will become clear why in a moment. Now we just need to accept that that's what we need. So the final Z, let's call Z bar, however you call that, is going to be a product between Z and another weight matrix. We are going to call it WO. And this one is going to be in LD1, which means that WO is element of R and heads times D2 by D1. So this means that in the end, I ended up with the matrix of the size of the one I started with. But and remember, what I started with is in each row, I had a representation of each token in the input in the order that came in. So now I just produced a new representation. Remember when I said, what is the goal? The goal was to produce from initial token value a new contextual representation. And that new contextual representation is captured in each of the rows of the resulting matrix. Yeah.
For the WO, that's C. That's going to be C tilde.
Yeah. Thank you. Yeah. Okay, a lot of work, but we got there, right? We managed to create these contextualized representations. So this is just a visualization of everything. Okay, let me see how much time we have. Is there anything else with the attention? Okay, so now we know what the self-attention is. Now we are going to start going remember how I started with, like, we have encoder, decoder. Encoder is a set of encoder blocks. And then I said each encoder block is consists of self-attention plus this feed-forward neural network, basically. So now we are going to start from the beginning, from input to the transformer. And then we're going to come to self-attention, breaking down what self-attention is now. And then we're just going to go over the entire step to finish understanding what the encoder is. You're going to take 2 minutes, come back at 2:30, and then we'll have just enough time to cover the position of encodings.
I had a question about the diversity semester.
Okay, yeah.
So are we like to dive into the specific LLM or just interpretability of LLMs?
Not a specific element, there isn't really anything special about any element itself versus a sales. So what we are going to cover is older techniques for sometimes you're going to start in there. Yeah, and then it's going to be like a mix of things, mostly but again,
Are we going to have a file, by the way, for this class? Because are we going to have like a plan file?
no, yeah.
Yeah, because you said like you have to make one assignment. Three was supposed to be, is now assignment 4, so
Oh, I meant, what
Yeah.
was it now assigned before?
Yeah.
Was when, yes,
Okay,
and then I want to do something else for
okay, thank you.
Okay, let's get into our transformers. So now I've needed to explain in lots of details what self-attention is, but now we are going back to zoomed out view of transformer, and we are going to go from input, right, to encoder, all the way to the end of the encoder, and then after that we are going to go to the decoder. Okay, so the left is encoder, the right is the decoder. So as I hinted, and as you might expect, the first layer is going to be layer where we have our embedding matrix and where we do token lookup. I also want to emphasize something before we go further. You know how with your deep averaging neural network you have written for your assignment, you have combined input token embeddings, and after that you have worked with a single vector, which is a representation of the entire input. Here with transformer, we are going to constantly work with a sequence of token embeddings, right? They're just going to get progressively complicated, but we won't have like one vector for the entire input. Rather, we are going to have and look at this all the times a sequence of vectors, as many as there are tokens in the input. So forget about that averaging stuff you have learned before when we go over transformer. Okay, so first thing, as always, you get a piece of text, you are going to tokenize it. And here, for example, detective investigated, you see how we have a subword tokenization going on. That's pretty standard with all of the LLMs today. Since 2017, basically, we have used subword tokenization. We are going to map them into vocabulary, and then the first layer is going to have those that embedding metrics. And the transformer, if we are training them from scratch, like we had in 2017, the embedding matrix is going to be randomly initialized matrix, and you would learn token embeddings together with the entire network, okay? But the principle is the same. Eventually, you get one static token embedding for each token in the input, and that's what we start with. And then you kind of construct the input like I did. X was L by size of the embeddings. We would likely also work with mini batches, so we would have a tensor. Batch size times L times the dimensionality. Now, I'm here starting to mention positional encoding. Anyone remembers why is it important to have, why something with position might be important? Yeah.
The position of words as was mentioned in the meaning, like interchangeable words can mean
Yeah. Exactly, right? Like language is sequential, and how we put words together, we were told matters, and it does, right? So in our models, we'll also have a capacity to understand whether dog eats, I don't know, chicken, or chicken eats dog. Is completely a different situation, right? So right now, with self-attention, I didn't mention anything about these, one token knowing in which position is the other, right? So we need to start encoding that information, and we need to start giving to the model some way of knowing which word came in which order, or at least relative positions, like how much this token, how far away is it from another token, which might be useful in attention, right? Like when we are doing those dot products, maybe we would calculate importance differently if we knew they were closer to each other or farther away from each other. So this is a topic in itself. I could have a whole lecture and more on positional encoding. Here is one categorization of them, and at the top, instead of embeddings, I should say encoding. So there are different ways of how people have gone about this. And I'm going to talk about three approaches. The most trivial one that has been used from 2017 for about 4 years, surprisingly to me, is that we just create an embedding for each position. So position, let's say maximum number of position we encode is 500. We would have from 0 to 500. For each one of these integers, we would have a high dimensional embedding representing and encoding that position. And then we would sum for each token, its token embedding in the input together with the embedding of its position. So if I had, I don't know, cat 8 mice. So here cat is 0, 1, 2. I have in my input layer embedding matrix of the size of the VOCA, right? And dimensionality. So in each row, as I have probed you many times in the course so far, we have an embedding for that token. So this is embedding for token index equals 0, right? But now with positional embeddings, you would also have another matrix of the size of maximum length that is a hyperparameters that the creators of the transformer architecture have chosen, times the same dimensionality D1. And when you produce our input representation for cat, you would take the embedding of cat plus embedding of position equals 0. Okay? That's how we did it for at least 4 years. What I really don't like about this is that position is an integer, and now you replace it with thousands numbers, which is kind of wacky way of going about things. It's really kind of brute forcey in a way. So first issue you need to encode and train lots of extra parameters. Maximum length times D1. These days we have ambitions to encode an entire book, if not many books. So sometimes we want to encode lengths of 100,000 tokens. So 100,000 times at least 1,000, lots of numbers again. And again, we are bounded by memory of GPUs, so that's quite wasteful. Another issue is that small perturbations in these tokens, in these embeddings, can cause large difference, right? Although 0 and 1 are completely discrete, tokens, and they mean very different things, then in this continuous space that might not be reflected. As we are bounded by memory, we are going to set maximum length to something that's not necessarily maximum length of what we would like to encode. And the final issue is that the embeddings of position, let's say 0 and 1, might be as different as the difference between the embedding of position 0 and 1,000, right? So there is no notion of which tokens are closer and which are farther away, which is another issue. Interestingly, the original architecture had proposed this sinusoidal positional encoding. So you need to be kind of sharp right now to see what's going on here. On this visualization, on x-axis, we are basically visualizing how we are going to produce an embedding for that position. And on y-axis, you see different sines and cosines based on, they're basically becoming progressively, have progressively increasing wavelengths. So when I choose, let me stop at one moment. So each dot here represent a value I'm going to place in a positional embedding of position. Right now I'm showing 36. So that means for position, let's say 0, I should be clear, super clear here. So for position 0, meaning token that appeared in the first place in the input text, I'm going to take even values in the embedding, positional embedding, are going to be drawn from a sign. And which particular sign function I'm going to take is determined by this value here, right? So if I'm taking the first dimension in the positional embedding of the first token in the text, I would use basically 0, I guess 0 over 1. It would be just a 0. And so on. So you can see here, each one of these dots is representing a draw from this sign function. And what's interesting, actually, if you do some trigonometric trickery, you would see that, and you could infer that these embeddings that are created like this and by original attention is all you need paper is added to the embedding of the corresponding token. Although the creators and authors of this paper have added it in the input to kind of indicate absolute position, actually these embeddings together are encoding relative position encoding. So comparison between let's say here, if I had embedding position 0, and then later I have another position, these embeddings will be more different for them than they are for the ones that are close to each other. When I say it's non-parametrics, it means there is no parameters you need to learn. Unlike here, where you had to learn all these parameters, here you are drawing from deterministic functions, and there's nothing to learn. You just choose these values, you put them in the input. So that's great, and values range from -1 to 1, which is also nice because typically these values in token embeddings are going to be small, so you don't want some enormous numbers to overtake the values that you have in embeddings, because then this addition wouldn't work. So that's the reason why, for example, just adding a vector with all that consists of just integers corresponding to the position, such as if the position was 200, and I have vectors of just repeating 200, if I add it here, and here mostly we have between 0 and 1, now this one becomes extremely dominant. So what's actually used today is something called rotary position embeddings, or ROP. And it's a very clever idea about how to ditch this addition altogether and include this information about when I'm using self-attention, integrating information about how far are two tokens together in a really neat way. And the way they do that is basically observing that, okay, by doing query key products, we are doing this product between corresponding queries and keys. Dot product mathematically is this, right? We take magnitudes of these vectors, and then we multiply with the cosine of corresponding angle between them. So this observe, well, if I want the dot product, and I want to increase the importance of tokens that appear close to each other, well, then I can manipulate this angle between them, and in this way manipulate the importance that comes out of the attention. And that's basically what they do. They are rotating these queries and keys such that these angles between closer things become smaller, and between farther away become bigger. And by doing that, they are encoding relative position in the transformer without introducing additional parameters or polluting the input space. Okay, so ROP, I will say this, and you can then, if I forget, which I have tendency to, I won't ask you this in the exam. This is a little bit more advanced and will require way more math to fully understand. The math itself is not complicated, and all it boils down in your attention matrix, you have a rotation matrix in the middle, but I won't evaluate you on this. It is important to know because this is how we encode position in transformer today in modern LLMs. Okay, let's stop here and then we are going to next time move forward with other bits and pieces of the transformer architecture.